Hi, and welcome to MSc. In this video, we're going to be looking at asymptotes and points of discontinuities. Specifically, we're going to be looking at it for a function that looks like this one. It looks like the ratio of two other functions, in this case, two parabolas. The right-hand side here is really a rational algebraic variable expression. This type of function is going to lead itself to often having asymptotes, when we'll look at that, as well as points of discontinuity. And these both result from exclusions in the denominator, values of x, for which this function is undefined. And looking at it in this format, it might be kind of hard to see where that comes from, but once we do some work to simplify it, it will become more apparent. We want to try to simplify this down, and we want to look for factors that are common in numerator and denominator to do so. The x squareds here can't be canceled because they're terms in the numerator and terms in the denominator. They're separated by plus and minus signs. What we're looking to do is find factors in the numerator and denominator. So let's start by factoring the numerator. And I can common factor out an x, and that will leave me with x plus 3. These are now factors in the numerator. The x is a factor, and x plus 3 is a factor. Don't forget, you can always go back and check your factoring by redistributing in, and so x times x is the x squared, x times 3 is the 3x. So these, one or both of them, could be canceled, depending what the denominator simplifies to. This is a trinomial, so we can use trinomial factoring, and we know we're looking for two numbers that will multiply to negative 12 and add to negative 1. And so we can say x, and we know that 4 and 3 will multiply to 12. They have a difference of 1, and if 4 is the negative, then that will work just fine. And again, you can refoil this out to make sure that things will work for you. And of course they will. Here's where we can also now list our restrictions. We know that x cannot equal the following. We can't have the denominator be equal to 0. So if this first bracket became 0, the whole denominator becomes 0, because it would be 0 times another number, and that would be undefined. In this case, if x were 4, 4 minus 4 is 0, so x cannot equal 4 in this equation. Additionally, if this bracket became 0, then we would have a case of an undefined value because of a 0 denominator. So x cannot equal negative 3. So these are our restrictions for this equation. We can now look at canceling. So unlike up here where these were terms, the x plus 3 and x plus 3, they are actually factors now. So I can actually remove those entirely. And I can then rewrite this as x over x minus 4 with two restrictions. X cannot equal negative 3 and 4. I'm reordering those in numerical order. That is not necessary. Again, default to whatever your teacher had prescribed for you to do at that point. So this is a much simplified equation than what we had above. And I'm going to show you a graph of this in a moment, and we'll talk about the different features. What we know here is that this function f of x will have an asymptote. And it will have an asymptote along a line. And we talk about asymptotes being along the line. It'll be along the line x equals 4. So we know that because the restriction that caused the x equals 4 is still present now in our simplified version. It's also going to have a point of discontinuity, which I'm going to abbreviate POD. It's going to have a point of discontinuity at x equals negative 3. And so that a point is at a value, not along of the line, and it is the restriction that canceled out. So points of discontinuity will always relate to the canceled restriction that's no longer present visually in our final simplified version, and the asymptote will always be the piece that is still there once you have fully simplified. So different questions can arise from this, and we'll look at some of them as I go through this example. If we had another equation, g at x, and let's say it was just equal to x over x minus 4. Well, the only restriction in this one is that x can't be 4. That would make the denominator 0. These two functions are not equivalent to one another. We cannot say that f at x is equivalent to g at x. All right, and the three-lined equal sign there is the equivalent. We can't say that that's true. Even though they simplify to the same value, this function f at x has an extra restriction. It has a point of discontinuity in it. So even though they simplify to the same value and their graphs will look the same, there is a point of discontinuity in the f at x. Let me show you on Desmos what this looks like. So on Desmos here, I've entered our original function, and here you can see it looks like the reciprocal function. And what's interesting here is if I look at x equals negative 3, pardon me, we get an undefined value. Because we know that x cannot equal negative 3 as we showed in the mathematics a moment ago. We can see the asymptote along the line x equals 4, and there is actually a horizontal asymptote along the line y equals 1 as well. If I look at the function that I called in the other equation, I called g at x, this one looks identical, right? You can actually see if I superimpose them, there's no difference, but this has a value at x equals negative 3, right? And so we can see that this has this value of 0.429. And so they are not equivalent. They are not equivalent functions. So jumping back over to my note, we can see if I import this graph, which of course continues on in all these directions, we can put some labels on here. This is the graph of f at x, not the g at x one that is not equivalent, but the f at x. And we can see that now we need to add a point of discontinuity at x equals negative 3, because this doesn't show up. And that's one of the notes, and maybe I should have mentioned this when we were on Desmos, because it's just 1 point, it's like less than a pixel, really, mathematically here on the image. So you often can't see the points of discontinuity. So if you're creating a graph, you want to add those points of discontinuity. So we'll add a point of discontinuity here. I'll draw a little circle, empty circle. So we'll move this over to the x equals 3. Now this scale is going up by 2, so the x equals 3 is right in the middle. And there it is. Again, this circle is much larger than the actual exclusion, right? Which is tiny, tiny, so small it doesn't actually show up. But we're trying to highlight that there's a point of discontinuity there at x equals negative 3. There's also some asymptotes. So if we're trying to sketch this graph out for a test or something, we'd want to add an asymptote. The asymptote is a vertical asymptote along the line x equals 4. And we also have an asymptote here horizontally, y equals 1. So let's add some labels here. So this is the line y equals, or I guess we could probably say f at x equals 1. And this is the asymptote along the line x equals 4. And of course we have our point of discontinuity at x equals negative 3, as I'd mentioned earlier. So this would be a pretty reasonable sketch of the graph that we have. We've indicated the horizontal asymptotes. We've added the point of discontinuity for our sketch. And so we've well represented f at x, again, which is not equivalent to g at x, because even though it would be identical in every way, it would not have that point of discontinuity. It would not have that hole in the graph. A couple extra things I'd like to do here with you for this example is to look at the domain and range of f at x. So looking at the domain and range here of f at x, the domain in these types of problems is often a lot easier than the range. So the domain, we have set builder notation, and we're adding restrictions. And the nice thing is we've already got our restrictions labeled right there, where x cannot equal negative 3 and 4. The range for this can sometimes take a little bit longer to do, and as you get more comfortable with this, things will move along a little faster. I'm using f as an element of the real numbers, where f cannot equal, and there's actually two values that it can't equal in this scenario. One is the horizontal asymptote. It cannot equal 1. And we can get that horizontal asymptote from graphing it, from experience looking at table of values. We can also look at kind of a limit approach, look at what happens when x gets really large and when x gets really big and negative. And in both cases, this is going to start to approach a value of 1. The other piece that we have is our point of discontinuity piece. And so our point of discontinuity has a value of 0.429. And we can get that as a fraction even by subbing in our restriction into our equation here. So if I subbed x equals -3 in to f at x, which we know is not formally allowed because it's been excluded, but here the limitation's gone. So if I tried to do that here and put f at -3, I would get -3 over -3 minus 4, and I'd get 3 over 7 being positive because the -3 over -7, the negatives would cancel. And so this is the decimal equivalent. That was from the value that showed up in Desmos when I hovered over the point. And y in this graph can actually never be that value because of our point of discontinuity. So this is how I can do it algebraically. You saw how I could do it with a digital tool such as Desmos. So sometimes calculating the points of discontinuity and asymptote behavior can take a little bit longer for the range of a function. The last piece I'll do here for this example is looking at the asymptotic end behaviors and redescribing those as a review. So we're going to have 4 statements as x approaches, and let's start with the 4 because that's the horizontal asymptote, that's the restriction here. We're going to say as x approaches 4, and I'm going to start with it from below. Then we're going to say the function f approaches, so as I approach 4 from a number less than 4, this is going to approach -infinity. And we can say that as x approaches 4 from above, f at x is going to approach infinity. And we can see that as I approach x equals 4 from a number larger than 4, it shoots up to infinity. We also have, though, our horizontal asymptote. So let's look at that. We can say that as x approaches -infinity, then f approaches 1. And it actually approaches 1 from a number less than 1. So we're going to put as a negative. And then we'll say as x approaches positive infinity, what does f do? Well, it still approaches 1, but approaches it from a number larger than 1. It comes down on top of it. So this is covering, I think, a fairly complete description of what we started with and what we can be asked of you in these types of problems, right? You can be asked to simplify and state restrictions. You could be asked whether or not it's equivalent to another function. You could be asked to sketch the function, right? And this has the general shape of a reciprocal function. You could be asked domain and range of the function you've been working with. You could be asked for the asymptote that results from the restriction or the point of discontinuity, and you can be asked to describe the asymptotic end behaviors. Again, will every question have all these parts? Probably not, but you should be able to do all of these pieces for the function that you're provided with. I hope that this video has been helpful. Please consider liking and subscribing if it has been. Thank you very much for listening and watching.